Hey guys, and welcome back to the Beginner's Guide to Restoring Early Tube-Based Black and White Televisions. Next couple installments are probably going to be kind of long and kind of heavy, because we're going to dive deep into theory, and troubleshooting, and trying to repair the vertical deflection circuit. Let's get to it. Alright, let's talk about the vertical oscillator. What does it do? Well, there are a few key requirements it has to meet. One is that when there is no incoming received signal, it will oscillate and provide a signal to the deflection amp and move that electron beam. You don't want to have your electron beam stationary, because it'll burn the phosphor. So, when the set's just sitting there, no signal attached, and you get that snow on the screen, this oscillator is running. It also needs to lock on to an incoming signal. And part of the requirement for doing that is when it's running on its own with no incoming signal, the frequency it runs at, called the free running frequency, needs to be pretty close to the incoming frequency. For the sake of argument, let's just say it's 60 hertz. Alright, there are two basic types of oscillator. Now, an oscillator is a circuit that is inherently unstable, meaning the output of it is going low, high, the voltage is going all over. And it does that because it has positive feedback. If you ever design an amplifier, say an audio amp, you want negative feedback to prevent things from going crazy. You get positive feedback, for example, when you put a microphone near the output of an amplified speaker, and it feeds back in. That's positive feedback, positive reinforcement, and that things will get out of control and start howling and screeching and blow out the speaker if it gets too crazy. So we want controlled chaos. We want this thing to be unstable but in a controlled manner. So we want to introduce some positive feedback. One way to do it is with a blocking transformer. That's not what this set uses. This set uses an RC coupled multivibrator. It seems like the higher end sets use the transformer version. I think it's because, as I've mentioned before, resistors, these carbon comp resistors, drift with temperature, as do the paper caps to some extent. So when the set warms up, the frequency can drift a bit in this. The blocking transformer, being an inductor, I don't think it's as susceptible to that. I'll just briefly show you what a schematic for a really basic blocking oscillator is. In the grid circuit, you have a transformer that is coupled to the output. So the signal from the output gets coupled back to the grid. Think of it like a tickler coil in a classic radio circuit. So this feeds back upon itself, coupled by a transformer. Okay, well, there's another way to do it. A multivibrator circuit, a classic circuit, be it transistor, tubes. So we have two identical triodes. Typically, you'd use a tube with two triodes, a 6SN7, a 12AU7, something like that. Something with two basic identical triodes. We're going to put a grid resistor in there, like a grid leak resistor, to provide a bias for the grid, meaning any current that trickles through this will create a voltage drop across it, which will self-bias the tube, and a plate load resistor going to a positive supply, and the cathodes are just grounded. Alright, so we have both of them set up like that. Really simple. We need to introduce some chaos, some feedback. How do we do that? We do that by cross-coupling the plates. So very simply, we take a connection, go onto this resistor, go over here, no connection, and we put a capacitor, go onto this grid. And then we do the same, go on the other way, no connection, and we put a capacitor in there. So what determines the frequency? The frequency is determined by these component values. So they will select these resistors. Well, one, you have to bias the tube correctly, and then you get an RC time constant between these resistors and these capacitors. Typically, all the values would be equal. Some rough starting values. We'll go with 100K and use 50K for these two guys, and something like 0.001 microfarad or 1,000 picofarad for these guys. So you can imagine component tolerances being what they are, say plus minus 10%, 20%. This is not going to be dead on 60 hertz. And as components age and whatnot, things drift. Now, of course, TVs have a vertical hold control. So what do? You make one of these variable. I'm not saying it's this one in particular, but you make a component in this circuit variable, which will alter the free running frequency. That's how you implement vertical hold. When the components have drifted off so much, they won't sync anymore. We'll get to the sync in a moment. So a very, very typical problem with these old sets is you can't get a vertical lock. First thing I would always try doing is replace these two caps. They might be mica, probably they're paper. So go after those and then check these resistors and replace any that are, heck, these days I would just go ahead and replace all this stuff and use metal film resistors, which are very stable, very temperature stable, and go with plastic film. A perfect world, maybe polystyrene caps if you can get them, because they are the most stable, or C0G ceramic or mica or plastic film. Any one of those will be better than the old paper caps. That's how our basic free running frequency works. The multivibrator works. Oh, and then where does your signal come off of? Pick it off of either plate and send that off to your output amplifier. Now, what does this waveform actually look like? Well, it depends where you pick it off. In some areas, it's close to a square wave. In other areas, it's close to a ramp. But it's not going to be perfect in either case. Will there be a little bit of wave shaping afterwards, RC coupling network, but that's the basic gist of it. So how do we sync? Well, here's an analogy for you. Imagine a kid gets on a swing and starts kicking his legs and shifting his center of mass to get that swing going. And then he gets a good pace going, gets a good rhythm going, and he's just swinging on his own. That would be like the free running oscillator. And suppose you come over behind him, kind of time things up, and give him a push. After a few pushes, you are now in control of his swing. That's how this works. Our sync pulse is a pulse that's going to come in here. Sake of argument, let's just say it's capacitively coupled, and we have a sync pulse coming in. What does that do? That disrupts the natural cycle of this and forces it to start triggering when this comes in. It'll charge the cap. It'll force the issue. In order for this to work, these need to be fairly close in frequency, because we're really just correcting the phase difference and to some extent the frequency. I don't know what the lock range is with this. Let's just, for sake of argument, say it's plus minus 5 hertz. So the free running frequency of this would have to be something like 55 to 65 hertz, and adjustable with this range. So with this range control, say you can vary it between this, and your incoming is 60. If with this control and all that, the best you can do is below 55 or greater than 65, it won't be enough for this sync pulse to correct it, to force the issue, let's say. Now you might be wondering, if everything's equal on both sides, how does this thing ever start oscillating in the first place? Simple. Nothing is perfect in this world. You will never find two absolutely identical triodes. You will never get match resistors to the nth decimal point that are exactly the same. And with the capacitors, one side will start conducting before the other. It will start sloshing back and forth as this thing heats up. I hope that made some sense. I think I simplified it as much as I could without losing some key details. If you want to know more about how exactly a multivibrator works or how you would select the component values, There is a wealth of resources online. This circuit's been around for ages. It's the heart of many, many, many oscillator projects. Get yourself a copy of the Grob book or any one of the other early TV theory books. We might as well just go right into the vertical amplifier. There's a schematic in Grob that is almost exactly what we see in our set, so I'm just going to show you that. So we pick off a signal at the appropriate point in our vertical oscillator. We couple it with a capacitor to the grid of our power vertical output amp tube. Resistor going to ground to provide a return path for the grid. We set the bias voltage with a resistor on the cathode and the cathode bypass cap. We can vary this resistor to set the operating point of the tube, which affects the vertical linearity. Plate goes right to the primary of an output transformer that goes to B+. And the secondary goes directly to the vertical yoke windings. And these resistors are there to prevent ringing, I do believe. That's really it. If you're wondering where is the height control, I believe this would be the height control, and you'd vary one of these to set the vertical hold. I'm going to assume you have some idea how to use basic test equipment. So what I did is I took my multimeter and put it on DC volts mode. This is auto ranging, so all I have to do is put DC volts. These probes are Cat 2 or Cat 3. They're good to 1,000 volts, so Cat 3, it says right here on the clip, max. So we're fine with that. You don't want to use a cheap meter that's only good for a couple hundred volts when you're working on a set that has upwards of 400 volts on some of the circuits. My meter has detachable alligator clips. I'm going to keep the one on the negative lead. The chassis on this set is ground. I'm just going to clip it right to the chassis in a convenient spot. Not the same with all TVs. Not all set TVs or radios have the chassis being ground. In some cases it's hot. It could be floating. In this case it's ground. It's safe. That's where they say to put your meter when you're making these tests. Other probe has a very sharp tip on the end. We're going to get down in here. I was going to do a couple of these, and I'll continue on and I'll write all my findings down on my printout. So let's start with the vertical output tube. If you don't see a reading, that means that tube pin, like 1 and 5, have nothing. There's nothing going to that. Not all these pins are used by this tube. Pin 2 should be ground. Pin 3 should be 245. So 1, 2, I can see 2 is just grounded right to the chassis, so of course that's going to be 0. Pin 3, over here, we have 252. It's right about, they said 245, 252, we're right in the zone, so that's great. That's sorted to pin 3, or pin 4 rather, so 3 and 4 measure the same. Pin 6 should be 300. This is pin 6. 175. Now I cheated and looked ahead, and that I know is influenced by the height control. So let me vary that. So we can go all the way down to 40 and all the way up to 217. Now they don't say on the service info where the control position is, I don't think. Sometimes they do. Let's see. Ah, here we go. All front controls except contrast at approximately half rotation. Well, I'm even at max, I'm not getting that voltage indicated. So let me put it halfway through. That'd be about here. And we're getting about half of what they say it should be, which makes sense. We're only getting half a deflection on the screen, so we know we have a problem there. We don't know what the problem is yet. We don't know where it might be yet. Well, we know it's in that, well, we presume it's in that circuit, but I mean, we don't know what the bad part is, but we know that there is a problem there. I'll keep going with the rest of the readings, then we'll switch to the scope and see if we can gain some insight. Alright, I finished going through the voltage checks. The rest of the voltages on the 6K6 tube were reasonable. The 6SN7 all the voltages were down a bit, between 30 to 50% lower than they should be. Now let's take a look at the output of that circuit now. Let's see what that shows us. So pin 2, again, clip this to the chassis. And let's get down in there. Pin 2, right there. It's got a bunch of stuff going to it. Alright, cool. And here's my trusty Tech 465. One of you asked me to do a tutorial on how to use a scope as part of this series. If I do it, I will do a separate video. This series is going to be long enough as it is. Plus, there are lots of tutorials online on how to use a scope. Alright, now it's flickering because we're at a fairly low frequency. But the waveform looks pretty darn similar. So, it's annoying that they don't show you the full thing on the screen at once, but let me try to get closer to what they show. Alright, that's pretty close. I just played around with the time base and the vertical settings. So they're just proportionally looking at it. My start point is about halfway up the waveform. Theirs looks to be about 1/3 up. So that's off a little bit. Also, mine is curved, and theirs is more of a straight line. Now, there is a linearity control on this. But that's on the output tube, so I'm tweaking it now. That doesn't make any difference. Now, just knowing these sets and knowing early electronics, we still have all these paper caps. When paper caps get leaky, this is the kind of thing you see in coupling caps or timing caps, is they distort the waveform. There's current leaking through where it shouldn't be, which drags things down, especially in high impedance circuits. So it doesn't really surprise me. Now, as far as the voltage, 60 volts peak to peak. I am on the 10 volts peak to peak scale. And let's get this here so we can count 1, 2, 3, 4, 5. We're at 50 volts peak to peak. So we're down a little bit. Down a little bit. But I wouldn't expect that to only fill half the screen. And if I adjust the height control, hey, it changes that. So max height, we now have 1, 2, 3, 4, 5. Now we have 60 volts peak to peak. And it's only filling half the screen, basically, slightly more than half the screen. And that curve is even more pronounced now. I suspect that's being caused by a leaky paper cap in that multivibrator circuit. Well, they gave us one other waveform to look at, so let's take a look at that. I'm going to put this on my highest range, which is 50 volts per division, and then switch over to pin 3 of the vertical output tube, the plate, which should be 340 volts peak to peak. Don't use your little USB pocket scope kind of thing on this. You will very likely damage it. Clip came off. Alright, there we go. Let's move this down. There is that nasty spike I was talking about. 50 volts per division. So 1, 2, 3, 4, 5, 6, 7. 7 times 5, 350 volts. They say it should be 340 volts. That's remarkably close, I think. But does it look like the waveform they show? No, it doesn't. No, it doesn't. I'll change the time base to get a little more like theirs. It looks quite a bit different. Their little spike here is, what, a third maybe of the overall height. Mine, it dominates. It's 80%, something like that. And again, we have a curve. Theirs is very straight. Now, I don't know where their ground reference is on this. I don't know if their ground is right at the bottom of this or is at the bottom of the screen. That part's a little annoying. But it definitely looks very different. Which again doesn't surprise me because we know we have a problem, so I wouldn't expect the waveform to be correct. Now, There's a few things we can check. One, well, let's look at the schematic and review. So here is our circuit. I've already verified that B plus is in the ballpark. It's around 350-ish volts. That's pretty close to being dead on. So we know that's not a problem. What else might be? Well, there's a problem with the vertical deflection amp. A really common source of the problem is this guy. It's a cathode bypass cap. It's exactly the same as with an NPN transistor amp where you have an emitter bypass cap. It serves the same function. If this cap is bad, it has a dramatic effect on the operation of this. Because this resistor between the cathode and ground sets the operating point of the tube. And notice that's with a linearity control in. These components here have a profound effect on the gain and the shape of the output because it alters. If you look at a response curve on a tube, this sets the operating point of it. Depending where you are on that curve, in other words, the grid bias changes how linear it is and how much gain you have. However, spoiler alert, I already swapped out that cap. It made no difference. But no, when you're at this in-between point where it's kind of working, then things get a little more subtle. It's going to very likely be one or more of these parts. Resistors have drifted high, paper caps are leaky, or the tubes are weak. Now, a simple thing we can do, I said I was going to try to do this without having a tube tester. We have two 6K6s in this set. There's another one used for the video amp. We have another 6SN7. It's used right over here in a sync pulse inverter. So we can swap tubes within the set. The odds of two tubes being bad in the same way are extremely low. You can also, of course, order yourself up some new tubes, but that's a simple way to eliminate that. If by swapping the tubes it looks different, maybe not right, but different, then you know you got an issue with one or both of your tubes. And you should look into getting some good replacements. If it works exactly the same with either tube, probably the tubes are okay. And what does my gut tell me from having worked on these sets before? It's these guys. So the output of our oscillator looked pretty good. It wasn't perfect, but if I turned the height up all the way, the amplitude was right and the shape was generally right. But we're getting something very bad out of this tube. It's a coupling cap, and it's a big one. It's 0.1 microfarad. It's pretty big as paper caps go. If that's leaky, it's going to distort the waveform driving the grid of the output tube. Similarly, this cap, this 0.05, is going off through this resistor over to the cathode. Either one or both of the, well, very likely both of these are leaky, both of these are bad. They're both going to have an impact on the waveform that's actually getting here. It's a shame they don't show us what the waveform is on the grid of the vertical output tube, but I'm guessing it's not correct. So, let's replace those two caps. Now, as to how do we replace them, well, unfortunately that's a little tricky in this case. The 0.1 that I really want to try replacing, it's in the back. It's this bumblebee cap back here. We have the 0.05 we also want to talk about replacing on top of it, and there's the 0.005. To get at this safely, easily, I really need to clip this out of the way, even if just temporarily. Prevailing wisdom is replace one part at a time, power the set back up. But more practically, when there are parts stacked on top of each other, I'm more inclined to replace both of these in one shot, and maybe this guy as well, because they are all interrelated. Now, in the interest of troubleshooting and moving things along, I'm either going to use J-hooks or just tack in new parts. I'm going to use a classic yellow, well, not classic, but the modern commonly available yellow axial caps. Alright, the set is on. Let's put our probe back in there. And I tell you, it doesn't really look right on the screen. Let's see, we're looking pin 3 in the vertical output tube. Nuts. That did not change anything. I am more than a little surprised. Okay, now what? Now I'm a little surprised that replacing 3 paper caps into electrolytics had seemingly zero effect whatsoever. I thought it would at least have some effect. And maybe it did, but it's too subtle to really see it. But it obviously did have a dramatic effect. So we haven't found the smoking gun yet. There is one more paper cap left down in here. The value of this is going to have a big effect on the frequency. But if it's leaky, the capacitance can be the same, but it can distort the waveform, so that's a possibility. I'm going to keep going with the paper caps. I mean, generally, from a practical point of view, when I work on these sets, say for a customer, I just blow through and replace all the paper caps, because they're always bad. But when I say bad, I mean tested at full rating with full 400 or 600 volts across it, the leakage is excessive. Plenty of times it doesn't matter. If it's a coupling cap, it might only have a few volts DC or a few tens of volts DC rather than 400. But all the .05s in this set are 400 or 400 volt rated. Why? Because they ordered a whole bunch of them. Doesn't mean that they have to be good up to 400 volts. Some of them are going to have a lot less. Or it's used as a bypass to filter noise out of a supply rail, something like that. It could be open, it could be very leaky, it's going to really have no effect. So there's plenty of times where these paper caps can be technically bad, but not have a bad impact on the circuit. That being said, it generally does improve things when you replace them. So let's get that guy out. It's .005. Just like these .05s, that's not a standard value these days. 0.1, yes, and 0.01 you can get. But back in the 60s-ish, late 50s, they switched over for a pretty good reason, actually. I'd say that for another discussion. Now you would use a .047 or a .0047, so that's what I'll use for that. And I'm going to start checking these resistors. You have to be careful when you check resistors while they're in circuit, because they might be connected to some other parts that affect the reading. I'll give you a real simple example. Here, it says deflection yoke has a couple resistors inside of it. 560 ohms in parallel with the windings. The windings are 68 ohms total, so on either side we're going to have 34 ohms. If you were trying to measure this resistor, it's going to measure around 34 ohms because it's in parallel with it. That's a much smaller value. In order to check this, you have to remove one leg of it, one end of it from the circuit, clip it out, unsolder it, disconnect it. Generally, if you're reading the value and it's on value or higher, trust the reading. If it's lower, drastically lower especially, do not trust the reading and clip it out. Why? Because there's really no other component you could have connected to a resistor that's going to make its value go up. Unless there's a capacitor that's still holding a charge. It still has some voltage on it. That can. So when in doubt, completely disconnect one end of the resistor. Well, I replaced that .005 and that did have an impact. We still have this really high spike, but this is looking a lot more linear now. Just linearity control. some minor effect, but that's looking a lot straighter. Show you the screen in a moment. It's filling more of it. It looks a little better. Let's look at the output of the vertical oscillator as well. Curious. Yeah, this is looking straighter too. A little bit. Yeah, that's looking better too, I think. If I cut the height down a little, add more of a bend to it down here. So it's getting better. It's getting better, but we're still not there. This is what the screen looks like now. That's with max height. So it's swung up a little bit more. Well, let's keep in mind this should not fill the screen from top to bottom. This is not a porthole set. It has a rectangular or a double D mask on the front of the set. But we're getting better. Now there's also a centering control. So if we get enough height that it was going from, say, here and clear off the top of the screen, we can shift the entire thing down. So we are getting close to where we want to be.